In a bamboo forest, growth doesn't creep along the way it does with most plants. Certain species can shoot up nearly a meter in a single day, an almost unsettling speed that makes bamboo one of the fastest growing organisms on the planet. Within 3 to 5 years, a stalk that started as a thin shoot poking through the soil is fully mature, strong enough to be harvested, strong enough to eventually become flooring, utensils, or, strangely enough, fabric soft enough to wear against your skin. That range, from rigid building material to soft, breathable textile, all starting from the exact same plant, is what makes this transformation worth understanding. If you've ever wondered how one raw material can split into such wildly different finished products, stick around, and if this kind of industrial detective work interests you, subscribing helps us keep making more of it. Because bamboo's journey splits into two completely separate paths, and both are genuinely fascinating. Harvesting begins with selecting mature stalks, something experienced cutters can judge almost instinctively by color, sound, and stalk rigidity. Younger bamboo is too soft and moisture-heavy for most industrial uses, so workers move through the grove selectively, cutting individual stalks rather than felling entire sections, a practice that actually helps bamboo forests regenerate faster than most other harvested plants, since the root system remains completely undisturbed underground. Once cut, the long stalks, sometimes stretching well over 10 meters, are trimmed of branches and leaves, then transported to a processing facility. At the facility, the raw stalks are cut down into manageable sections, and this is where the two pathways begin to genuinely diverge, even though they start from identical raw material. For the mechanical route, the one that eventually produces flooring, cutting boards, and solid utensils, sections of bamboo are split lengthwise using heavy blade machinery, dividing the round stalk into flat strips. These strips still carry the bamboo's natural outer skin and inner pith, along with a significant amount of natural starches and sugars trapped within the plant fibers. Left untreated, those starches make the material a magnet for insects and mold, so the strips go through a boiling process, submerged in large tanks of hot water, sometimes with a mild alkaline solution added, for several hours. This boiling step pulls the natural sugars and starches out of the fibrous structure, leaving behind bamboo strips that are far more stable, resistant to pests, and less prone to warping or cracking later. After boiling, the strips are dried, either in open air or inside industrial kilns, with carefully controlled temperature and humidity, reducing moisture content down to a precise target, usually somewhere around 8 to 10%. Dry too fast and the strips crack. Dry too slow and mold risk climbs right back up. Once properly dried, the strips are sorted by color and grain quality, since natural variation between individual stalks means no two strips look quite identical. This meticulous sorting phase is crucial because bamboo is a natural product with dramatic color gradients. The outer layers of the stalk, which receive the most sunlight, are naturally darker and denser than the pale, soft inner layers. Sorters manually categorize the dried strips into distinct color groups ranging from light blonde to caramelized amber to ensure that a finished floor or cutting board has a uniform appearance rather than a chaotic, mismatched pattern. In addition to color, workers check for structural defects such as hairline splits, deep knots, or uneven thickness that occurred during the drying kiln phase. Any strips failing this visual and physical inspection are immediately routed away to be pulverized for composite building materials and fuel. From here, strips destined for flooring go through a lamination process. Multiple strips are stacked and pressed together under intense heat and pressure, using food-safe or low-formaldehyde adhesives, fusing them into thick, dense boards. Depending on how the strips are oriented during pressing, either flat, edge grain, or strand woven where fibers are compressed under extreme pressure into an incredibly dense block, the resulting board takes on different hardness characteristics. Strand woven bamboo, in particular, ends up harder than most hardwood flooring on the market, a genuinely surprising outcome from a plant that's technically a grass, not a tree at all. These pressed boards then move through planing and sanding machines, smoothing the surface to an exact thickness tolerance, followed by cutting into standardized plank sizes. A protective finish, often a water-based lacquer or natural oil. Bamboo utensils and cutting boards follow a similar early path, boiled and dried strips. But instead of lamination into flooring-sized boards, the material gets shaped through cutting, carving, and sanding machinery into spoons, forks, bowls, and cutting surfaces, finished with food, safe mineral oil to protect against moisture absorption during everyday kitchen use. The second pathway, the one leading toward fabric, abandons the mechanical route almost entirely and instead relies on chemistry to break bamboo down at a molecular level. This process produces what's known as bamboo viscose, or in more refined production methods, bamboo lyocell. For viscose production, raw bamboo is first crushed and shredded into small chips, then cooked in a sodium hydroxide solution, essentially caustic soda, dissolving the plant's cellulose structure out of the surrounding lignin and hemicellulose. This produces a thick brownish pulp, sometimes called alkali cellulose, which gets pressed to remove excess liquid and then shredded further into fine crumbs to increase surface area for the next chemical stage. These cellulose crumbs are then treated with carbon disulfide, converting the material into a compound called cellulose xanthate, which dissolves into a thick, honey-colored viscous liquid, the very substance that gives viscose its name. This liquid gets filtered meticulously to remove any undissolved particles, since even microscopic impurities can cause weak points or breaks later when the fiber gets stretched thin. The viscous solution is then forced through a spinneret, a metal disc punched with thousands of tiny holes, essentially the same concept as a shower head, except instead of water, thin streams of dissolved cellulose emerge. These streams are extruded directly into a chemical bath containing sulfuric acid, which instantly regenerates the cellulose back into solid form, hardening those thin streams into continuous filaments of bamboo fiber the moment they hit the acid. This transformation happens remarkably fast, liquid to solid fiber in a matter of seconds as it passes through the bath. The newly formed filaments are then washed thoroughly to remove any residual chemical traces, stretched to align the internal fiber structure and increase strength, and finally cut or wound onto spools, depending on whether the end product will be spun into yarn or used as continuous filament fiber. Lyocell production, considered the more environmentally refined version of this chemical pathway, uses a different solvent, N-methylmorpholine N oxide, which dissolves bamboo cellulose directly without the intermediate xanthate stage. And critically, that solvent gets recovered and reused in a closed-loop system rather than discharged as chemical waste, significantly reducing the environmental footprint compared to conventional viscose processing. This clean-loop system is a massive technological leap forward for sustainable textile manufacturing. In traditional viscose production, the toxic chemicals used in the bath often end up as hazardous wastewater that requires extensive treatment before disposal. The lyocell method, however, recovers up to 99% of the solvent, continually recycling it back into the beginning of the dissolution process with virtually zero waste released into the surrounding ecosystem. Once spun into yarn, whichever chemical pathway was used, the bamboo fiber moves to textile mills, woven or knitted into fabric using standard textile machinery. The resulting material carries genuinely distinctive properties: naturally breathable, moisture-wicking, and remarkably soft against skin, largely because the fiber's cross-section under a microscope is covered in micro-gaps and grooves that regular cotton simply doesn't have, allowing better airflow and moisture absorption. Stand back and look at both pathways together, and it's genuinely remarkable that a single plant, cut from the same forest, splits into a rock-hard flooring plank on one side and a fabric soft enough to sleep on the other, with the only difference being whether the material was shaped mechanically or dissolved chemically and rebuilt from scratch. So think about the last bamboo product you actually touched, whether it was a cutting board or a t-shirt. Did you realize it came from the exact same raw stalk as its polar opposite counterpart? Let us know your guess in the comments. And if these hidden industrial splits fascinate you, subscribe, because one more transformation is still coming.